Hello, everybody. Thank you for attending our event tonight. We're very pleased to have Arshia Jacob here. Arshia has completed her PhD in Max Planck Institute for Radioastronomy in Bonn and has now moved to Baltimore, Maryland, where she's attending, she's at Johns Hopkins University, and she's continuing the work that she has done in Bonn and much more advanced. And so she's going to talk a little bit about this type of work and what can be learned from studying hydrides molecules. So thank you for attending. And if you have any questions or anything, you just put it in the chat and then we can address these questions either during the talk or during the discussion session. And Arshia will be happy to answer any questions you have. And so please just grab a drink or something and just relax. And then Arshia has a wonderful presentation for you. Arshia, hello.
Hi, thanks a lot, Craig. So let me just share my screen. I hope you can see it. Everything's good?
Yep.
Great. So at the offset, thanks a lot to Craig and the other organizers for inviting me to give a talk on a topic that's very dear to me. So without further ado, I'd like to talk to you about unveiling the mysteries of the chemical universe using small molecules. So taking a closer look at the background image, what you see here is this wonderful star-forming region called W51, named after Westerlund's catalog, and it was the 51st source that they had identified. What you see here in blue are the different stars, but between all of these blue specks, you see a lot of dynamics and structure in shades of green and red. So all of this basically tells us that the space between stars is not empty, but highly inhomogeneous and complex. Now, this space and the stuff between stars is called the interstellar medium, or the ISM for short, which is what I refer to it from now on as. And it's mainly composed of gas in the form of hydrogen and helium, as well as trace abundances of heavier species. So here I've shown you the periodic table as seen by observers in space. So we have larger sizes for different atoms or elements, showing you their relative abundances. So for example, hydrogen is the most abundant, followed by helium, and then you have the remaining heavier species, which we collectively call metals. In addition to gas, we also have dust, as well as magnetic fields and radiation fields, not only from the stars themselves, but also from cosmic rays, X-rays, etc. There are also other components or constituents of the interstellar medium, such as turbulence, etc. But what we are mainly focused on is the gas, because the gas plays a very essential role or a key role in the life cycle of the interstellar medium. Now, this life cycle begins with diffuse clouds or diffuse material, which is very dilute, which accumulates matter to form translucent and dense clouds, more about which has already been talked about in Stefano's Astronomy on Tap talk, which you can go check out. Now, over time, as these dense clouds collapse, they form protostellar systems, which eventually become stellar systems, much like our solar system, with a central star and planets surrounding it. Now, over time, as the central star evolves, it begins to burn heavier nuclei within its core, such as hydrogen into helium and then helium into carbon and so on, until eventually it explodes via supernova explosion and replenishes the interstellar medium back with its energy and mass, thereby recycling it and making this a cyclic process. Now, because the diffuse regions form an essential link between the death and birth of stars, making them important reservoirs for material, they're also ideal laboratories to study interstellar chemistry. Now, broadly, we can distinguish between the stages prior to star formation, that is, the diffuse, translucent, and dense clouds, from those stages that are post-star formation based on their physical conditions, namely the temperature. So the stages prior to star formation are much cooler environments as opposed to those once the star is formed, which is far, far hotter. So this in turn requires different wavelengths to observe the radiation that is emitted, and in turn different instruments. So this brings me to the topic of using different observational techniques and the need for multi-wavelength astronomical studies. So if you take a look here at this wonderful example of M51, also known as the Whirlpool galaxy for obvious reasons, because as you see here, this galaxy has this fantastic whirlpool-like spiral arm structure. So if you look at the farthest right image, what you see is the optical emission from stars, which is wonderful, but all you see is starlight. But if you move towards the infrared, you begin to see cooler stars as well as dust. And once you go into the radio, you're actually probing the densest environments, and you see a clear concentration of the material within the center. So this clearly tells us that different wavelengths probe different environments, and in order to have a complete picture of the environments that we study or the astronomical objects that we study, we require a multi-wavelength approach. Now, this is also another topic that was covered by the University of Cologne's very own Vina in another Astronomy on Tap event. But this similarly brings me to a different problem, which is we require different molecules to trace different environments, because each of these different molecules in turn tells us something different. So sticking on to our example of M51 or the Whirlpool galaxy, if you look at the molecular gas, which is on the left, you see that most of the emission or the radiation that you see is concentrated in the densest parts of the center and in the very densest parts of the spiral arms. But if you move towards the atomic gas, it's much more diffuse and separated and widespread. And if you look at the ionized gas, it's somewhere in between. So different molecules or species trace different environments or exist in different gas layers based on their chemical pathways, based on how they're formed and destroyed. And so a complete picture, once again, requires the combination of all of these different species. Now, how do we observe these species? Well, we actually use something called spectra, which I dub as chemical fingerprints, because each of these different molecules or atoms are excited either via its electronic excitations or via its rotational and vibrational motion, which gives rise to a release of energy. Now, this energy is unique to each atom or molecule depending on the different transitions, and has been widely studied in the laboratory by different groups around the world, especially the one in Cologne, who have made immense efforts in measuring accurate frequencies for these different transitions. Now, using this information, us observers begin to observe or look for these transitions in space. And what we see, well, most of you are familiar with this picture of the emission spectrum. But what we actually observe are the same information converted in terms of intensities and line widths. Now, using this technique, we've detected over 240 molecules in space, excluding the isotopologues or the rarer species of these molecules. And we've observed everything from diatomic molecules all the way to fullerenes with around 60 atoms formed in the shape of a buckyball. So now you tell me, well, this is all well and good, and you have this nice little coin collection of sorts of different molecules. But why do we need to keep observing or looking for these different species? Well, there are a few reasons. Now, the more complex species actually tells us things about life as we know it, the complexities, and begin to answer questions related to our own life. But the smaller molecules, which probe the primary stages or the preliminary parts of stellar astrochemistry, tells us about how things begin, which gives us a completely different picture. But overall, once again, based on the spectra that we observe, whether we see things that are more intense than expected, more wider than expected, or less intense and narrower, we can tell a different picture, or we can paint a different picture about the astronomical object that we're observing. So these molecules are essentially a tool that helps us peer into the inner workings of these astronomical objects. Now, I told you earlier in one of my introductory slides that hydrogen is everywhere. So with hydrogen everywhere, we should be able to unlock the mysteries of the universe, and then, well, game over, we've solved everything, we know it all. But if only this was the case, unfortunately so. So hydrogen mainly exists either in its atomic form or its molecular form as H2. Now, the former can be directly observed via its transitions at 21 centimeters, but the latter, molecular hydrogen, being that it's homonuclear, where you have two very symmetric hydrogen atoms covalently bonded, is very difficult to observe at radio wavelengths. So at these wavelengths, the problem is that hydrogen does not emit, which is ironic because hydrogen is the main constituent of this space. Now, these challenges are overcome by using proxies for H2, and the most commonly used proxy is CO, which is naturally used because it's the second most abundant molecule in space. So now the question arises of how well the combination of atomic hydrogen and molecular hydrogen traced by CO traces the total neutral gas column. Well, in order to address this, several different astronomers have observed or benchmarked it against other tracers of the total gas column, namely the dust emission. So when they compared the total dust emission with that of the total gas trace using atomic and molecular hydrogen traced by CO, they found such a residual map. Now, this residual map tells us that there is some excess gas, which came to be known as dark gas, which should be noted is unrelated to dark matter. Now, this dark gas, so I was basically talking to you about the challenges in observing hydrogen in space, because molecular hydrogen, being as it is homonuclear and symmetric, does not radiate at radio wavelengths, which is ironic because it's the main composition of molecular material in the cold environments. But anyway, we overcome this challenge by using other tracers of H2, namely in this case CO, which is the second most abundant molecule in space. But the question now is, how well do we trace the total neutral gas column by using a combination of atomic and molecular gas? Well, in order to benchmark this, different astronomers have compared the thermal dust emission, which is also a great tool for probing the total neutral gas, with that of H1 traced by the 21 centimeter transition and H2 traced by CO. So what they observed was this residual map, which showed us that there was indeed some excess gas, which was not traced by the combination of H1 and H2 traced by CO. Now, this excess gas came to be known as dark gas, which is unrelated to dark matter. But so now the new question became, what is the main composition of this dark gas? Well, it could either be atomic hydrogen or it could be molecular hydrogen. So the gas missing from atomic hydrogen can be relatively easily accounted for using absorption measurements, which means that most of this dark gas was in the form of molecular material. So at this stage, I'd like you to revisualize the cycle or the gas life cycle that I had shown you in a cyclic diagram in the form of a slab. And this structure is often known as a photon-dominated region or a PDR. Now, the PDR basically describes the interface between ionized and molecular gas. And so as you move away from the star, you begin to see that the ions begin to recombine to form atoms, which then collide to form molecules. So the different regions demarcated here are the different cloud transitions that I had discussed previously. So from this diagram, it is clear that there does exist a region in which molecular hydrogen is dominant, but we don't see that much CO. Now, this is because the self-shielding of CO, as we move into the more diffuse and dilute material, begins to weaken. And so it gets photodissociated, and this urges the need for new tracers of this gas phase. Now, we can also revisualize this problem in the form of a chemical model in which you have the relative abundances of the species plotted on the y-axis against the total gas columns. And if you follow the dark red curve, which shows you the hydrogen, molecular hydrogen abundance, and then the purple and blue curves, you see that the CO abundance begins to decrease, and there is indeed a region in which CO photodissociates, and it's no longer the main molecule containing the carbon budget. And so we require, once again, a new tracer for this gas phase. Well, this is where my specialties come into play. And what better molecules to use than hydrides? Well, what are they? Hydrides are basically small molecules in which you have a heavy element covalently bonded to one or more hydrogen atoms. So from a historical point of view, they're of immense importance, given that they were one of the first molecules to be detected in space as early as 1937 at optical wavelengths, and later they were also detected at radio, submillimeter, and far infrared. So highlighted in this plot are, well, a few of my favorite hydrides. But from an astronomical point of view and an astrochemical point of view, they're of immense importance, given that they're one of the first molecules to be formed directly from atoms and ions, making them the building blocks for more larger and complex species in the interstellar medium. So using this information, we go forward and we use one particular hydride, that is CH, to look at the Milky Way through its eyes. So CH is of particular importance, given that it has a tight correlation with H2, as was established using optical and UV observations. However, these observations are limited to nearby objects, which are extremely bright. Now, we tried to extend this analysis to overgalactic scales by using different transition of CH, that of its rotational lines at 2006 gigahertz or 2 terahertz, highlighted here in this energy level diagram in blue. And what we used was a very, very special instrument known as SOFIA, or the Stratospheric Observatory for Infrared Astronomy, and in particular, which in itself is a NASA Boeing 747, with a telescope attached to it. Now, in particular, we used an instrument known as GREAT, which is the German receiver for astronomy at terahertz frequencies. And well, it is indeed a space mission, or much like it. Now, moving into the actual science that we did, what we observed was widespread absorption. So here we have the example towards a star-forming region located at the very center of the galactic, of the Milky Way. And we see absorption not only at velocities that correspond to the velocity of this molecular cloud, Sagittarius B2, but we also see a lot of components at different velocities. Now, absorption spectroscopy in itself is a very robust tool for measuring the amount of material contained in any given column, because all you require is the relative intensities. Now, with information about the Milky Way's spiral arm structure, we can further assign the different velocity components that you see here as arising from different spiral arms, which truly makes this a study over galactic scales. And so this is exactly what we did. We observed several different star-forming regions, which also probes different spiral arms. And then we studied the radial distribution of the CH column densities. Now, the column densities are simply the amount of material that is traced in any given volume. So what we have here is the amount of material traced as seen by CH, plotted against galactocentric distances, which is basically the distance from the galactic center, starting at 0 all the way up to 12 kiloparsecs. Now, plotted in the dashed red line is the position of the sun or the solar system, and the different colored bands in the background represent different spiral arm crossings. So what you see is this odd double-peaked profile rather than a nice gradient. Now, this odd shape is actually not surprising because most of the molecular material, at least by mass, is concentrated within these regions. Now, we can further compare this to other tracers of the molecular gas, such as those of CO and C+. Now, these observations were carried out by Pineda and collaborators towards 500 lines of sight as a part of the GOT C+ survey or the GOT C+ survey. And if you follow the red curve, you see that the total column that was traced using C+ is comparable to the total column that was traced using CH. Now, this is exciting because you can use CH as an alternative tracer for C+, because C+ has the disadvantage that it traces several different phases of the ISM. Now, this problem of CO dark H2 gas is also well illustrated here in this plot, because if you follow the gray curve, which shows you the amount of molecular material seen by CO, it doesn't match the total estimated column that is actually present for the total molecular gas. So this gap is what we fill using CH. Now, moving on to a slightly different problem and a different molecule, which is still associated, is the hunt for CH2. Now, CH2 and CH are both formed and destroyed via similar chemical pathways. However, models have also predicted that there should be high abundances of CH2 in regions where you expect CH, namely in the diffuse and translucent clouds. But till date, unlike the ubiquitous CH, there have been very few detections of CH2. Now, why is this so? Well, this is partly because of the structure of the molecule. So it has very widely spaced energy levels, which make it very difficult to detect its lines from the from ground-based telescopes. But nonetheless, CH2 has been detected via its 68 to 71 gigahertz transition between the 4 to 3 levels, as you see here. And we are going to take a closer look at this. Now, this transition was originally detected by Hollis and collaborators almost 3 decades ago. And here we have their wonderful detection towards Orion KL. Now, these detections were made towards very hot cores, which are simply hot and dense regions. Now, this is slightly a paradox, because we would expect CH2 to exist in regions associated with CH-bearing clouds, and we just saw that CH is associated with the more diffuse and translucent material. Furthermore, this molecule was not detected when pointed using larger telescopes with smaller beams towards the same position in the sky. So is the chemistry wrong? Or is CH2 not really detected here at all? So where does this emission really come from? What did they see? Now, we attempted to answer this question, but I'll quickly take a slight detour to tell you a fun fact. Now, Gerhard Herzberg was a Nobel Prize winner in chemistry in 1971, who was awarded the prize for his lifetime achievements in the field. He also obtained the very first laboratory spectrum for CH2, but early on in his career, he had misidentified the CH2 transitions, which later became identified as coming from methane, which is now a very popular band that is observed in comets. So later in his memoirs, he recollected that the rightful identification of CH2 is one of 2 discoveries that stands out in his career, as finding it gave him a great deal of satisfaction. So what we are looking for is a similarly satisfying answer to look for where the CH2 really comes from. So going back on track and looking at the observations, we reobserved what Hollis and collaborators had originally detected using the same telescope, which was the Kitt Peak telescope located in Arizona. So we reobserved the position that they observed, which is the nominal Orion KL, which is a very dense hot core. But we also observed different positions within this region, which are marked here. And we detected CH2, a signal in CH2 towards all of these different places. So what does this tell us? It tells us that the emission is extended. And furthermore, if you take a closer look at the intensity of the emission, we see that the intensities towards this nominal position are far weaker in comparison to those which are further away. So this tells us that indeed this emission could be depleted within the hot core. But another hint that this gives us is that the large beam size of the Kitt Peak telescope may contain contributions from neighboring regions, as shown here from the yellow contours, which mark the C+ emission. So in order to verify this, we used a slightly smaller telescope with a slightly larger telescope with a smaller beam called Onsala. Now, from the outside, this looks like a giant golf ball, but it's actually a nice dome which encloses a 20-meter telescope. So the beam size of the Onsala telescope is roughly half the size of the Kitt Peak telescope. And what we observed were the same positions once again. And what you see is that towards the nominal position, which is now position marked 2, we see no emission whatsoever. But if you move slightly away and towards the regions where the C+ emission peaks, following the contours in yellow, we begin to see a signal for CH2. So this confirms our hypothesis and tells us that CH2 is indeed associated with a different gas layer, which is not dense at all. So chemistry prevails and everything's fine and the observations are consistent. So this places both CH2 and CH in this nice diffuse translucent band within our PDR structure. Now, so far I've only talked about molecular gas and I've told you nothing about the atomic gas. Well, what about it? So as you see from this image, the atomic gas layers are not purely atomic. You have a lot of ions and electrons. Moreover, atomic hydrogen is everywhere, so it's not the best tracer for tracing purely atomic gas. So the question now is if a molecule or if a hydride can be a better tracer for atomic gas than atomic hydrogen itself. Well, the simple answer is yes. Now, to show you this, I'd like to take another detour and ask you a different question. Well, can noble gases form molecules? And you would laugh and tell me, well, Arshia, we all know that noble gases are rightfully named so because they have a completely filled outer electronic shell and they have no need for forming molecules. Well, that's true on the Earth's surface and in its atmosphere because we don't detect any naturally occurring noble gas molecules. But of course, as with anything, it's possible to synthesize this in the lab. And furthermore, under the extreme conditions of space, you can easily ionize these atoms and force them to form molecules. Now, this is arguably one of the highlights of the Herschel mission or the Herschel Space Observatory when it detected the first noble gas-bearing molecule, argonium or ARH+, in space towards, you guessed it, the Crab Nebula. Now, they detected it via 2 of its transitions in emission, and you'd think, well, is this exotic molecule everywhere, or is it only observed towards such exotic regions as the Crab Nebula? Now, it was previously also observed in absorption towards Sagittarius B2M, if you remember our previous example, but it was not identified. Now, that's because, if you remember previously, we saw very deep absorption at the velocities of the molecular cloud, which are now missing. Now, why is this so? Well, before we get into the reasons why we don't see any absorption here, astronomers were not able to identify it, partly because of this mystery, but also because on the Earth's surface or in its atmosphere, argon-40 is its most abundant isotope. But in space, argon-36 is the most abundant isotope, so we were looking for the wrong isotope the whole time. Anyway, problem solved. We know that this is indeed from argon-36 and corresponds to the argonium spectrum. But why don't we see anything here? And what makes argonium an ideal tracer for the atomic gas? Well, before that, I have this cliffhanger right here, which asks exotic molecules and where to find them. Well, the answer is that they're everywhere. They're ubiquitous. And we also extended observations towards this or observations of this molecule using the Atacama Pathfinder experiment or the APEX 12-meter telescope. So coming back to the answer that we were looking for, well, the chemistry once again tells us why. Now, argonium requires hydrogen or molecular hydrogen for its formation and destruction, which means that for there to be sufficient amounts of H2 for its formation and destruction, for there to be sufficient amounts of argonium that we can observe, it must exist in regions which are purely atomic. Now, this is verified both with observations and chemical models. And so it forms, ironically, a better tracer for the atomic gas than atomic hydrogen itself. So I've hopefully convinced you of the big impact that these small molecules have, because I've shown you that they trace different transitions and the distribution of different phases of the interstellar medium, which provides us insights into the origins of interstellar chemistry and also gives us constraints on star formation. There's far more on my to-do list. For example, I'm currently working on HyGal, which stands for Hydraides of the Galaxy, a Sophia legacy program which characterizes the Hydraides in the galactic ISM, using observations of very different Hydraides towards many different sources within the galaxy. And of course, as always, there are more molecules yet to be detected, both big and small. So keep looking. Thank you.
Thank you very much, Arshia. That was a wonderful presentation.
Thank you.
Thank you to everyone who has stuck around for the end. Sorry for the technical difficulty, but now I'm in the pub. If you have any questions, please put them in the chat and then we can ask them. This will flow very nicely. First of all, I guess I wanted to say hi, Gal. I like the name that you chose for Hydraides of the Galaxy. Very similar to the Herschel program.
Right. Hi, Gals with an I and hi, Gals with a Y.
Is there a story behind your last slide? What is among us, Arshia?
Molecules.
Wow.
It's very deep.
Do we have questions?
Yeah. So I'll start the questioning then.
Go right ahead.
The one that I had was you showed this image of the CO dark gas.
Right. I can go back there.
My apologies, this is so far.
No, no worries.
Good to start from the beginning. Or
Right.
close to. So is there a reason for this asymmetry? Because we're looking at the galactic center. Why is there such an asymmetry with the CO dark gas?
Well, it's not so much an asymmetry, but rather we're seeing things that are less dense. So it's the regions that are not probed by the dense gas. So it's everything in between the star-forming regions. So of course, this is also slightly biased by the thermal dust emission that we compare it with. So yeah.
Thank you.
No worries.
Yeah, so another question I had was just with the magnetic fields, which is important for ISM analysis. Yes. How do hydrides help with detecting magnetic fields, or do they?
Well, actually, that's an interesting question because OH and CH both have Zeeman splitting, so from which you can determine the magnetic field, so the line strength along any line of sight components, which is one of the few ways you can determine the magnetic field so far. But CH is a far trickier problem, but OH is very widely used. So yeah, hydrides are multi-purpose. They're not only tracers of gas components and gas phases, but they can also tell you far more about the environment, like in this case, magnetic fields.
Great, thank you. We have a question from the audience from Rebecca Aladro. What about heavier hydrides, such as like CH3 or CH4?
Yes, I mean, they're mainly detected in comets and cometary systems. So I don't know very much about CH3 detections or how how long-lived this molecule is in stellar systems, or sorry, star-forming regions. But it's widely detected in comets. And I personally haven't analyzed any data related to them, but yeah.
You talked about a lot of, CH and CH2 and argonium. Are there any other hydrides that might be useful for determining ISM physics?
Right. So if we go back to, go forward, it's a little bit more. I had shown you a plot. Yes, here it is. So this basically tells you the year of detection against the number of hydrides detected. But you notice that a few of them are differently colored. And I said that these were my favorite. But so if you look at OH plus and H2O plus, the chemistry of these molecules are actually initiated once again cosmic rays, similar to argonium. So they're also very good tracers for the cosmic ray ionization rate, and also very good tracers for atomic gas. Similarly, OH is also a very good tracer for the denser, for the more diffuse molecular gas in the interstellar medium. So different hydrides actually trace very different environments. SH, for example, traces turbulence and shocks. So if you spend enough time and you can combine all of the information that the hydrides tell you, which is the goal of the HyGAL project, you can actually map or trace the different phases of the interstellar medium. So that distribution is what we're trying to achieve through this project.
Wonderful.
Nice. By the way, Arshia, is it a real diagram or is it just a chemical version of Space Invaders? That's what it looks like to me.
Coincidence, right? The network, yeah.
Yeah, and maybe you just found out your favorite molecules from here because you're just playing Space Invaders and that's what got left, I guess.
True. I mean, it would seem suspicious if I made the diagram, but sadly, it's... or maybe Brett had the same idea when he made it.
Oh, we have to email them then.
Find out more.
But I had a question too. You talked about tracers in one part of your presentation. Right. What exactly would be tracers for? I mean, of course, I know what a tracer is. I work in the same thing, but just to hear from you and in your very clear style, what would a tracer be, and what does it help us to observe, and maybe also does it just trace the presence of another molecule, or also how it moves?
Right. So a tracer is basically any molecular or chemical species, I would say, because we use dust also as a tracer for molecular hydrogen, as I just showed you, is any species that we think coexists or is in similar environments. So it's, I think proxy could be a better term, because you can often get a proxy for things, right? So it's, in a sense, the same as what we mean when I say, or I mean when I say CO is a good tracer for H2. So it follows H2, or wherever there's H2, you can form CO, because H2 is also a progenitor species, which is necessary for the formation of all of these other chemical compounds, right?
Right.
And whether it traces the dynamics, that's slightly more complex, because as I said, with the example of atomic hydrogen, it's everywhere. Even molecular hydrogen is vastly spread out. So these different molecules are not as vastly spread out. So for example, I showed you that CO has weaker self-shielding. So it traces certain aspects of the dynamics, so the kinematics, but not completely, which is why, once again, we need all of these different molecules for a complete picture.
Right.
So yeah, you can't just stop at one.
Yeah. More funding, please.
So maybe one more question. You mentioned that CH and CH2 can trace these neutral regions,
yes,
around 100 Kelvin. Are there any hydrides that would exist in hotter regions closer to the ionization front?
Yes, so SH, even ionized hydrides. For example, there's CH+, there is SH+, which require higher energies for their formation. So this has been a long-standing puzzle called the CH+ puzzle, where we believe that it has to be formed in regions where you have the dissipation of turbulence or shocks, which drives the chemistry for these molecules to form, which in turn means that they're formed in regions which are very, very hot, which eventually get dissipated, but it's still much hotter environments than, let's say, 100 Kelvin. So the energy that you need is around 4,000 Kelvin to form these molecules. And their very high abundances that is observed was what brought about this mystery, because it was unexpected.
Right. I don't see any other questions. Maybe another one. I just want to ask you about the Milky Way model that you showed.
Right.
With the spiral arms, and how is this determined, or how well is it known? How accurate is this image?
Right. So there are, this is adapted from Greaves and Williams' 1994 paper. And we've used the latest spiral arm models, which follows like a log spiral structure for determining the different arms. But you can simply do this using trigonometry. So you can just use basic geometry to determine the positions and velocities based on the distance between the sun and the galactic center and your object. So if you know the angle and the distances, everything becomes very easy. So there are, of course, uncertainties in how wide each spiral arm is. So for convenience, we always assume that their distribution is equal across the entire spiral arm, which is not necessarily the case, as you know, modeling all of this. But sometimes I think this is an acceptable assumption to make. So it's all right.
And so this the trigonometry, this is with the stars or the stellar sources, or with the gas?
Oh, with the star forming
gas.
region. So for example, if you, so if you have
so has Gaia really helped with this analysis?
To determine distances, of course.
It's much newer than 1994. But,
oh, yes.
And then there's this whole issue of the parallax and the high error in the parallax, but
exactly.
Gaia issues is something else. Yeah.
Yeah, but Craig, when you modeling people come, you just ask these, really mathematical questions for some reason. The real issue here is, have you ever tasted any of the molecules here, Arshia, that you talked about?
Well, I mean, specifically any of the molecules, no. But I wouldn't suggest tasting hydrides like HCl for our own good.
Oh, yeah. I hope there are certain school kids here that are listening to this, because HCl is really found not just in space, but also in certain school labs. So please stay away from HCl. Yeah.
Don't try this at home.
Yes.
But I mean, ethanol is a common, commonly consumed item. Which a lot of people are aware of what it tastes like, but yeah, like Craig.
Oh.
But sorry.
Oh no, I'm just really excited now. Finally, somebody said yes.
Yes, we know what it tastes like.
We've tried this in every episode for a long time.
Well, you assume that it tastes the same, right? Or
yeah,
you hope.
Great. So I think these are all the questions we have. I mean, there's more comments in the YouTube video if you want to look at them. Many people are saying, well done and congratulations. And too many names to list. Sorry, but yeah, you can see them on the YouTube video. And I really like your PDR image.
Thank
I
you.
might have to ask you for it at some point.
Sure.
By the way, if there are too many names to list, to all of those names, please donate to us, because when you donate to us, we will be more interested in saying out your name aloud. We will soon start a Patreon.
The true businessman amongst us.
Yes.
And so thank you everyone for sticking this long. And we have, as always, we have our Astro News segment given by Parade. So if you want to stick around for this would be wonderful. And Parade has something interesting to talk about as well. And Arshia, you're welcome to stay as well.
Yeah.
Please.
I hope you do, because molecules coming up. Okay, let's go. Well, I would say the world has a lot to say. I am just but a medium. But yeah, after all this serious chemical chatter, let's bring you the exciting astro news for this past month. We will again scare you with more climate news, but let's just go with it for some time with some nice astro stuff. Okay, guess who got a good smashing? Jupiter, of course, the one true planet that eats asteroids for breakfast. Brazilian astronomer Jose Luis Pereira, who was just casually making a video of the transit of Jupiter's moon Io, you know, as you do on a normal Monday evening, captured this live action sequence, which you can see in a video here. I will show you the video. I hope you can see it. Yeah, there's a flash here. Anyway, so as half of the world slept, yeah, which is nearly always the case, so don't feel guilty. Oh, please open your mics. This is just but a discussion. A wide alert was issued immediately to amateur and pro astronomers across the world through the Jovian bolides detection project. That is real. 9 more astronomers observed the ensuing impact and data that they had just observed and were still observing, making it the first time so many people observed the same phenomenon. And this is according to reports. It could be wrong that it was the first time, but yeah, it grabs more eyes. Because I observe Jupiter every night with my eagle eyes and I didn't see anything. I'm not sure. Such an impact reminds us, of course, of the famous Comet Shoemaker-Levy 9, which they say was a sizable media circus and honestly very interesting. Scientifically, because researchers were able to deduce the composition and structure of the comet. The collision basically left dust floating on the top of Jupiter's clouds. By watching the dust spread across the planet, scientists were able to track high altitude winds on Jupiter for the first time. And even magnetosphere. So by comparing changes in the magnetosphere with changes in the atmosphere following the impact, scientists were able to study the relationship between them. All of the details are here for you. It was actually observed on September the 13th, around nighttime here in Europe. All the information you need, for example, the Jovian latitude and longitude is given here in case you want to search vigorously about this. Based on data, the object was not that big as Shoemaker-Levy, which was, I think, kilometers wide, but this was just 20 meters, but still created this big, huge impact that you just saw, and supposed to be a remnant of a larger comet or asteroid, and broke up in Jupiter's gravity. So let's do our duty and watch planets during the night and during dinner instead of Netflix. Such interesting things happen. Scientists now say that such collisions, though not always observed, are common. So you have a good chance of observing one. Actually, it's just like when Craig sees the planet smashers and runs to collide with them. You must be confused, but Craig knows what I'm talking about, right, Craig?
Yeah.
No, you're not. Because the Planet Smashers, of course, are a Canadian ska punk band from Montreal, Craig. Isn't that the story of how you started loving astronomy? Honestly.
Yeah. Just a young kid in Canada listening to them.
To the Planet Smashers. Please say it aloud. Don't be afraid.
Planet Smashers.
Yes. This is not an advertisement for Planet Smashers. This is just an appraisal of Craig's really innocent childhood. Of course, nobody knows about the Planet Smashers. I do in terms of comets, but nobody else because it's a band from Canada. Anyway, moving on. Sorry. I'm not sure which slide you see. Oh, yeah. Latest news from the comet world, since we are still talking about it. It is, again, honestly fascinating. I will try to tell you 24837020005 QN173. That's the name of the comet. Really easy. It was discovered to be active on July 7th this year in data obtained by the Asteroid Terrestrial Impact Last Alert System, ATLAS Survey Telescope. This is not how acronyms work, whoever wrote this. Now, what is in, the object was at a heliocentric distance of 2.4 AU approximately and exhibiting a thin, straight dust tail. What is so interesting about that? The interesting part is that it is an active comet, which means that out of more than half a million or so asteroids in the asteroid belt, about 8 of them have been confirmed to be icy and have been ejecting dust into space, which is typical of comets. You guessed right. The authors say that this object is interesting because of the blurring of the boundary between what were previously thought to be two completely separate types of objects, asteroids and comets. Asteroids are supposed to be metallic and comets are supposed to be icy. This is just a short, small detail that you might want to remember. Now this extremely narrow tail, maybe you can spot it here.